Hello, welcome to the lesson on probability. This is ITE 1812 Mathematics for IT. We will first look at the learning outcomes. So by the end of this lesson, you should be able to define the terms event, elementary event, compound event for a random experiment, and compute probability on any experiment, and also to identify mutually exclusive events and apply basic theorem on probability. And finally, to identify an independent event. So getting introduced to probability, starting with the basics. So the concept of probability allows us to make guesses on matters, but these are not wild guesses. These are informative guesses on matters where either full facts are not known or there is uncertainty about the outcomes. So this is what we try to do using the concepts of probability. We will start with getting to know the terminology. First, what we call an experiment. This is an operation or a process that can result in two or more outcomes. This is what we identify as an experiment. So some examples provided here. For example, tossing a fair coin is an experiment where the outcome, head or tail, is unpredictable. So when the coin is fair. Another example, rolling an unbiased die in an experiment, where the number that is to appear on the face of the die is unpredictable and subject to change. We don't know what will happen. And next term is random experiment. So this is any well-defined process of observing a given chance phenomena through a series of trials. So this can have finite or infinite number of trials, which each of them leads to a single outcome. Take some examples. Drawing a ball from a bag containing a given number of red, green, and yellow balls. So you might have seen this kind of examples during previous classes or even at school. Simple probabilistic experiments, random experiments. So what we have here, a bag containing multicolored balls, for example. So this can be identified. Drawing a ball from such a bag can be identified as a random experiment. And also drawing a card from a pack of 52 playing cards is also another random experiment. And then the term sample space. This is the set of all possible outcomes of a random experiment. So it is usually denoted as capital S. Example, assume that we toss a dice once and look at the result. The sample space in that case is 1, 2, 3, 4, 5, 6, because any possible outcome. These are the all possible outcomes at any given trial. Another example, sample of a random experiment conducted by tossing 3 coins at the same time. So any combination can happen. There are defined combinations that can occur. For example, 3 heads, head, tail, head, tail, tail, head, and so on. So you can get the different combinations in this case. So these belong to the sample space of this random experiment. And then an event. Let's try to define this. Let S be the sample space of a random experiment. Then any subset of S is called an event. Thus, an event is a set of possible outcomes. So the sample space can have multiple possible outcomes. You should also note that empty set is also an event. So for example, the subset head, tail, head, 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 tail, tail, head, head represent the events that give exactly 2 heads when tossing a coin thrice. So in all those examples, all those instances, there are 2 heads. And Now we introduce elementary event. This is a simple event which has single possible outcome of an experiment. So another characteristic of this elementary event is it cannot be subdivided into a combination of other events. So this is the simplest form. For example, throwing a die and the event of getting 6 is a simple event. This is not a combination of events. And now introducing compound event. When two or more events occur in connection with each other, then their simultaneous occurrence is called a compound event. The compound event is an aggregate of simple events. Example, when we roll 2 dice, then the event of getting 6 on either the first or the second die is a compound event. So it's a combination of events. That's why we call it compound. Now we will define event space. The set of all subsets of a sample space associated with the random experiment is called the event space of that experiment. So let's take an example right away. Consider the random experiment that toss a coin twice and observe the sequence of heads and tails appearing. Then the corresponding sample space for this experiment is head, 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 tail, tail, head, and tail, tail. So this is the set containing that. We call it the sample space. And we can define the event space as follows, including the empty set, head, 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 tail, tail, head, tail, tail, head, head, tail, tail, head, head, tail, head, and so on. So this is the set of all subsets of the sample space. That's what we identify as the event space. So now we introduce mutually exclusive events. So two events are said to be mutually exclusive if the occurrence of one event does not affect on the other event. So they cannot occur simultaneously on a signal trial. So one does not affect the other event. So if that is the case, we call them mutually exclusive events. So as such, when two events A and B are mutually exclusive, the A intersection B is null, corresponds to null set, because we don't have any components in there. So example, toss a coin 3 times and observe the sequence of heads and tails that appears. The sample space S consists of 8 elements, 3 heads, head, head, tail, head, and so on. Let A be the event that 2 or more heads appear consecutively, and B is the event that the tosses are all either heads or tails. So 2 separate events. So A includes 3 heads, head, head, tail, and tail, head, head. 2 heads appear consecutively in those instances. And B includes 3 heads or 3 tails. So when you take the intersection between A and B, you find that head, 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 3 head instance includes in the intersection. So it is not the empty sets, in other words. So we have to conclude that A and B are not mutually exclusive because their intersection has some elements. Okay, now we introduce probability more formally. So it is a numerical measure between 0 and 1 that describes the likelihood that event will occur. So now we have identified what are the events, event space, sample space, and all those concepts. Now we try to understand probability. So probability is closer to 1 indicate that the event is more likely to happen, and probability is close to 0, otherwise it's less likely to happen. So we now introduce the classical definition of probability. So the probability of an event A, denoted by PA, defined as number of outcomes favorable to event divided by total number of outcomes. So this is the basic definition or the classical definition of probability. Example, if an ordinary die is tossed, there are 6 possible outcomes. 1, 2, 3, 4, 5, 6. These 6 outcomes are mutually exclusive, since 2 or more faces cannot be turned up simultaneously. So if the die is fair, the 6 outcomes are equally likely. Therefore, each of the probabilities are equal to 1 over 6. Any of the value getting, for the probability of getting any of the values from 1 to 6 is 1 over 6. The probability of that an even number will appear when the die is tossed is 3 over 6, because we have 3 occurrences where we will get even numbers. So that simplifies to 1 over 2, 0.5. And now we introduce the frequency definition of probability. So in a random experiment where n number of trials are conducted, out of those n outcomes, only k outcomes are favorable to event A. So let's have this assumption. So the probability of occurring event A, denoted as PA, is given by limit when n reaches infinity, k over n. So this is the frequency definition. Now we introduce axiomatic definition of probability. So we take a sample space S associated with an experiment. So in this sample space, to every event A, so A is a subset of S, so we assign a number, probability of A, denoted by P within brackets A, is called the probability of A, so that the following axioms hold. So we define 3 axioms here. Number 1 is probability of A is greater than or equal to 0. That's axiom number 1. And axiom number 2 is about the sample space. Probability of S, PS, is equal to 1. All the combination, all summation of all the probabilities will be equal to 1. So that is denoted by PS. Axiom 3 tells us if there are multiple events, A1, A2, and so on, so these are a sequence of pairwise mutually exclusive events within S, so that the intersection of all these events are having no elements. That means they are empty sets. Then probability of A intersection, A1 intersection, A2 intersection A3, and so on is equal to the summation of all the probabilities taken separately. That means PA1 plus PA2 plus PA3 and so on. So these are the 3 axioms that we introduce regarding probability. So we have an example here. So we have a table showing the percentage frequency table for the petrol brand most preferred by 50 motorists. So we have 4 brands here: BP, Caltex, Engen, and Shell. So you have the counts in the second column and the percentages of those petrol brands in the third column. So question number 1 in part A is asking what is the probability that a randomly selected motorist prefers Engen. And second part is what is the probability of finding a motorist who prefers either the BP, Caltex, Engen, or Shell brand of petrol. So let's see how we approach these solutions for these problems. Right, so for part A, let A be the event. So we define an event A, that motorist who prefers Engen petrol. So then PA we can define to be 6 over 50, because we have the count 6 for engine petrol brand. So the total number of people would be 50. So out of that, 6 prefer engine. So the probability PA is 6 over 50, which is 0.12. Thus, there is only 12% chance. So this is a 12% chance of finding a motorist who prefers engine petrol brand. Right. So that's the first part. And second part, we are asked to find the probability of finding a motorist who prefers either of these 4 brands. Right. So let A1 be the event that motorist who prefers BP, A2 prefers Caltex, A3 event that motorist who prefers Engine, and similarly A4 motorist who prefers Shell brand. So these are 4 separate events now. These 4 events represent the collectively set of events for the variable petrol brand preferred. So 4 separate brands. So we need to find the probability of PA1 plus PA2 plus PA3 and PA4 separately taken. Okay. So if we get these values separately, we know that we will get 1. Right. So therefore, there's complete certainty that a randomly chosen motorist will prefer one of these 4 petrol brands. So they are included in within this 4 brands that are stated here. Now, with that, we move on to basic theorems in probability. 15.1 theorem of probability. The probability of the null event happening is 0. So symbolically, P of null event is 0. Next theorem, let A and B any 2 events of an event space E corresponding to a sample space S associated with a random experiment E such that A is a subset of B, then PA, the probability of event A is less than or equal to PB because A is a subset of B. Next theorem, let A and B be any 2 events of an event space E corresponding to a sample space S associated with a random experiment E. So we now try to define the probability of P A union B. Probability of A union B is equal to, so this is given in the theorem, is equal to probability of A plus probability of B minus probability of the intersection. B probability of A intersection B. So this is 3 important theorems related to probability. Moving on with the corollary. So we expand this for 3 events, A, B, and C. P probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus the whole intersection between 3 events A, B, and C. P probability of A intersection B intersection C. So this is a corollary connecting these 3 separate events A, B, and C. So we have an example here. So Professor Jackson in charge of a program to prepare people for a high school equivalency exam. Records show that 80% of the students need to work in math, 70% need to work in English, and 55% need to work in both areas. So we have English, math, and that's a number representing the both areas. So the first question is, are the events need math and needs English mutually exclusive? So let's see how that approach in the solution. So these events are not mutually exclusive because some students need to work in both areas, right? So it is given in the problem that 55% of the students need to work in both areas. So you cannot define them as mutually exclusive events. Now, part B is compute the probability that a student selected at random needs math or needs English. So for this, we define a set A. We define an event A that students need work in maths, and B be the event that students need work in English. So what we are required to calculate is the probability of A union B. That means an O relationship, right? So compute the probability that student needs, that a student selected at random needs math or needs English. So it's an O relationship, which means we need to take the union relationship. So we need to calculate P, that is probability of A union B. So how do we get that? According to the theorem, it is equal to PA plus PB minus PA, the intersection B. So you have the values separately for these. Probability of A is 0.8, probability of B is 0.7, and probability of A intersection B is 0.55. So when you do the simplification, you get P A union B is equal to 0.95. So when the student is selected at random, the chance of he or she needs math or needs English is 0.95 or 95% in this case. Now we introduce another concept, which is complement of an event. The complement of event A is the event that A does not occur. Basically, we can call it the inverse or the opposite. So A event, we have an event A. We can also define an event where A does not happen, that we call complement of A. It is denoted by AC, superscript C, designate the complement of event A. So we have further relationships when it comes to complement of an event. That is, number one is probability of A plus probability of complement of A is equal to 1, right? That is, in saying general terms, and chance of a certain event happening plus some chance of a certain event not happening should be equal to 1. So number two is probability of event A does not occur is equal to the probability of complement of A. It is equal to 1 minus probability of A. So it is deriving from the first relationship. So this is the concept of complement of an event and related probabilistic relationships. So here we introduce one more example. The probability that a college student who has not received a flu shot will get the flu shot is 0.45. We are asked to calculate the probability that a college student will not get the flu if the student has not had the flu shot. So in this case, we have probability of will get the flu is 0.45. So the probability of will not get the flu is equal to 1 minus probability of will get the flu. So this is basically 1 minus 0.45, which is equal to 0.55. So this is a pretty straightforward example of the complement, the use of complement of event. And now we define dependent and independent events. So the question of dependence or independence of events is relevant when the experiments are consecutive and not simultaneous. So one happens after the other. So we have an example here. In tossing an unbiased coin, a trial is not affected by the result of the previous subsequent trials. So in this case, these events are independent. So we have what we call the multiplication rule for statistically independent events. So if we identify that two events, A and B, are statistically independent, then we can apply multiplication rule to find out probability of the intersection of A and B. And it is given by P A intersection B is equal to PA times PB. So where PA intersection B is the joint probability, we call it the joint probability of A and B. And PA is the probability of A only, and PB is the probability of B only. We describe that and try to understand using an example. Suppose you are going to throw two fair dice. So what is the probability of getting 5 on each die? Okay, so here we approach the solution like this. Let A be the event of getting a 5 on first die, and B be the event of getting a 5 on the second die. There are 6 faces on a die, and on a fair die, each is equally likely to come up when you throw a die. So you have 6 outcomes. It is equally likely. So therefore, PA is equal to PB is equal to 1 over 6. It is one of the 6 outcomes. So the two events, A and B, are independent using multiplication rule for statistically independent events. So PA intersection B is equal to PA times PB, which is 1 over 6 times 1 over 6. So ultimately you get 1 over 36. Because these events are independent, A and B are independent, you can just multiply the two individual probabilities to get the ultimate value for PA intersection B. So that's how we approach this solution. With that, we conclude the session, the lesson for probability. So in the next lesson, we will be covering further concepts in probability, that is conditional probability and Bayes' theorem. Thank you.